thank you very much for inviting me here today. And I'm happy to share some of the research that I and many other people have been doing on numerical development. When I started doing research on numerical development 40 years ago, there wasn't a great deal known, but it's really changed a great deal. And today the field is very exciting and going in many different interesting directions. And in particular, I'm going to be talking about the development of numerical magnitudes, which I think is the common core of a wide range of numerical development. So you can see how broad this area of numerical development is by looking at all of these major areas. So not 1 month goes by without interesting new articles coming out in every one of these areas. So there's research every month on the brain basis of numerical development, the evolutionary basis, infants' understanding of numbers, non-symbolic and symbolic representations of numbers, and I'll be explaining what those mean in a little bit. Counting, whole number arithmetic and rational number arithmetic, individual differences in numerical learning, dyscalculia, difficulty in dealing with numbers, cultural differences in numerical understanding, emotional influences of factors like anxiety, relations to basic cognitive processes, relations to other concepts that are quantitative, such as space and time, and interventions aimed at improving children's and adults' understanding of numbers. There's so many different research areas that sometimes we ask ourselves, is any theoretical integration justified? There was a great British historian named Arnold Toynbee in an earlier generation. He worked in the 1930s, 40s, 50s. And he asked a question about history that can be applied to psychological development. And just paraphrasing, inserting in development for where he had history, we can ask ourselves his question: does development have unifying themes, or is it just one damn thing after another? So is there any unity to what's going on in numerical development, or is it just a vast multiplicity of different particular developments? Now, I believe, as Toynbee did about history, that psychological development, and in particular numerical development, does have a unifying theme. And this unifying theme that I'm going to be talking about throughout the talk today is the growth of numerical magnitude representations. And I believe that this development provides a unifying theme for theories of numerical development. So one initial question we need to ask ourselves is, what are numerical magnitudes? And the answer is numerical magnitudes are the sizes of numbers. And people possess both non-symbolic and symbolic numerical magnitude representations. And let me illustrate what each of those mean by the tasks that are used to assess this type of understanding. So here's a typical task used to assess non-symbolic magnitude understanding. People or other animals, it's done with all kinds of animals, chickens, pigeons, rats, monkeys, human infants, human children, human adults, are presented dot displays, different colors, and they're asked or reinforced for choosing the more numerous display. So there are a certain number of yellow dots, a certain number of blue dots, and the question is, are there more yellow dots or blue dots? And the correct answer, of course, is that there are more yellow dots, even though the area that is subsumed of the blue dots is actually a little bigger in this display. And the perimeter is also a little bigger of the blue dots. But for number, there's more of the yellow dots. And the degree to which people and other animals can discriminate small ratios between different numbers of dots is the typical task used to assess non-symbolic magnitude understanding. And people get better at this with age. A wide range of animals are pretty good at this. Some animals, such as families in the animals in the Corvidae family, which are large black birds like crows and ravens and magpies, are actually better than people are at this task. But it's a very interesting task used very widely throughout the world. Here's a symbolic comparison problem that's exactly equivalent to the non-symbolic. It asks, which is more, 21 or 15? So in the previous display, there were 21 yellow dots and 15 blue dots. Here, we're just giving the symbolic number, 21 or 15. Now, both non-symbolic and symbolic magnitudes activate different predictable areas of the brain, and pretty much the same areas of the brain. Not entirely, because the symbolic magnitudes also activate linguistic areas, as you might expect. The non-symbolic areas, not as much. But these two areas that are circled in white are left and right intraparietal sulcus, and that area is kind of numerical magnitude central. It's very important in pretty much any numerical task. It doesn't matter if it's arithmetic or magnitude comparison or whatever numerical. In fact, even if there's no task, if you just show people dots or numbers in display, like you put the number 37 on the screen, these areas of the brain light up. So they're very important in magnitude processing. So we can ask, why is development of numerical magnitude knowledge a useful unifying theme? So one reason is that many species, including people, represent non-symbolic and symbolic numerical magnitudes in similar ways, horizontally on a mental number line, with the left side tending in almost all cultures and with almost all animals having the small end of the numerical continuum and the right side having the larger end. Now you might ask, why would the small end be on the left and the large end on the right? No one knows, but it's extremely reliable. There's some reports that in a couple of cultures, maybe they have the small numbers on the right and the large numbers on the left. But there's a lot of disagreement about that. There's no disagreement that in the vast majority of species and cultures, the mental number line is oriented horizontally and from small numbers on the left to large numbers on the right. Another advantage of focusing on numerical magnitude knowledge is that it allows unification of numerical development across all ages and all kinds of real numbers, whole numbers, fractions, decimals, percentages, negatives, etc. So this idea can be studied with all different kinds of numbers and all different kinds of ages. A third reason why numerical magnitude knowledge is a useful unifying theme for theories of development is that individual differences in numerical magnitude knowledge correlate substantially with important outcomes, including arithmetic proficiency and overall math achievement. Michael Schneider did a pair of meta-analyses of two related literatures, one number line estimation, one magnitude comparison, and found in both cases consistent relations between how good people were in discriminating magnitudes and how good they were overall in math. And then a final advantage is that acquiring more precise numerical magnitude knowledge promotes acquisitions of other numerical skills, notably arithmetic. And this finding has guided effective educational interventions as shown by the Romani and Siegler 2008 and the Fazio, Kennedy, and Siegler 2016 studies, and another by Braithwaite and Siegler in 2020. And I'll be talking more about these interventions later in the talk. So the first main part of the talk is going to be about the development of whole number magnitudes. And the first study that I did in this area was jointly with John Opfer in 2003. We looked at second, fourth, and sixth graders and undergraduates. Each person was presented 0 to 100 and 0 to 1,000 number lines. These are physical number lines rather than mental number lines. And I'll show that task in a minute. And they were shown one number per number line. So here's how this task goes. It's a task we use often throughout this series of research studies. So typical problem. Number line is presented with boundaries at both ends, 0 at one end, 1,000 at the other end. The number line is arranged from left to right to parallel the mental number line. And the child or adult is asked, where does 87 go? And then they're given a new number line that has 0 to 1,000, but no mark on it. And it might ask, where does 768 go? And we sample throughout the numerical range to get a sense of the function relating people's subjective estimates of numbers and the number's actual magnitude. Here are the results that Siegler and Opfer 2003 obtained. So one striking result was that the ideal here would be to have a linear function where you'd have 1,000 as a presented number and 1,000 as a median estimate at this point on the top right, and 750 and 750 and 500 and 500 and so on. But in fact, the function of the second graders on these 0 to 1,000 number lines didn't look much like that at all, but it did fit very well to a logarithmic function. So you can see that the logarithmic function accounted for 95% of the variance in these second graders' estimates. Here are the same data for fourth graders. Now, the fourth graders' data are interesting because the logarithmic function fits almost as well for the group. But when we looked at the individual functions, unlike the second graders, where almost all the individual second graders adhered to this logarithmic function, a little more than half of the fourth graders did, and a little less than fourth produced linear functions. And the linear functions look like this, which is with the sixth graders. So you see, this is what people are supposed to do on this task. This is what, if you understand numerical magnitudes and the task, you would do. So the bigger the number presented, the bigger the median estimate, and the function is linear. And here the linear function, both with individuals and with the group, accounts for pretty much all the variance. So it takes a while to learn this for the 0 to 1,000 numerical scale. Something interesting that we've discovered, and many other people have contributed to this, is that there's a similar developmental transition from logarithmic functions to linear functions that happens at different ages for different numerical scales. So we, and I suspect most people, would have guessed that once you understand the linear function being the right one, that you would apply it widely. But that isn't actually what happens. Development is much more piecemeal. So for the 0 to 10 range, 3 and 4-year-olds generate a logarithmic function, and 5 and 6-year-olds a linear one. Bertoletti found this in Italy, Muldoon found this in Ireland. 0 to 100, many people have found this logarithmic at age 6, linear at age 8. 0 to 1,000, you just saw those data a minute ago, logarithmic at age 8, linear at age 11. And Clarissa Thompson and John Opfer found that 0 to 10,000, 9-year-olds generate a logarithmic pattern and 12-year-olds a linear pattern. So development repeats itself at different ages for different numerical scales. So we learn these scales at different times, presumably as we encounter them more in school and arithmetic and other tasks, we get a sense of how big those numbers are. Another very pervasive finding has been that the linearity of the magnitude representation, so how close you are to a linear function, how well the linear function fits your estimates, is pretty highly correlated with your performance on a variety of other tasks. So Booth and Siegler, 2006, looked at second and fourth graders, and they related the linearity of the task of 3 different kinds of magnitude estimates. Actually, doesn't matter for our purposes what they were, but they're different tasks you can use to overall math achievement. And as you can see, pretty substantial correlations at both second grade age, so at about 7 or 8, and fourth grade, 9 or 10, with overall math achievement on all 3 of these tasks. Now, findings like these raise the question, well, how do children acquire a linear representation of whole number magnitudes in the first place? Because the logarithmic representation is more natural. Even chickens and pigeons and monkeys show logarithmic functions unless you train them for thousands of trials to do the linear function. They can do it, but it's not natural to them at all. They really prefer the logarithmic one. So we ask, well, how in the world does any human acquire a linear function for any numerical magnitude? So one pretty obvious contributor is counting. And counting provides many good cues to the magnitude of numbers. So when you count, even when you're just counting, say, a row of 10 objects, say 10 coins, and you're going from left to right, the higher you count, the bigger the number is. So it takes longer time to get there. So it takes longer to get to 8 than to 4. And it takes a bigger spatial movement from where you started to where you're going. And it takes more words and more physical motions if you're pointing with your fingers to get to bigger numbers than smaller numbers. We also started thinking, we being Geetha Ramani and I, that playing numerical board games may also contribute. Now, this is a game that, as far as I know, isn't played in Japan, but it's pretty common in many other countries. It was invented in India a very, very long time ago. Depending on who you believe, it was either invented about 200 BC or 1000 AD. I guess there was a subsequent game that was more like the modern game of chutes and ladders. And it was called Snakes and Ladders in India. And there was a kind of religious and novelistic overlay to the game. But this is how the game looks. This is the US and British version. And what you do is you start at the bottom left with the number 1, and then you spin the spinner and you make progress. And in the children's version of the game, the usual version, there are ladders that are good outcomes where you can go faster in a positive direction toward higher numbers. And there are also bad things that happen. There are these chutes where you can go down. And the shoots make children very unhappy because sometimes they've gotten almost to the end where they're about to win the game, and then they fall in a shoot, and it sometimes is only a minor setback, but sometimes it's a huge setback. And we started thinking about this game and realized that even though it may not have been designed to teach numbers, it actually, if they had been thinking about that, it would have been a brilliant way to go about teaching numerical magnitudes. Because the greater the number a token reaches, so let's just think about the very bottom row going from 1 to 10. So the greater the number a token reaches, the token is the piece that they move along the squares, the greater the number of discrete movements the child has made, the greater the number of number names the child has spoken, the greater the distance from the beginning of the row, the left side row, that the child has moved the token, and also the greater the time spent playing the game. And we reasoned that playing number board games provides visuospatial, kinesthetic, auditory, and temporal, that is time-based, cues to numerical magnitudes, because all these cues converge on the idea that 8 is not only bigger than 4, for example, but that it's twice as big because it takes twice as much time to get there. You've moved twice as big a distance, you've pointed twice as often, and you have said twice as many words. So to test this idea, we designed a numerical board game, which we called The Great Race, where a rabbit and a bear are chasing each other. And the idea is that they go from 1 to 10, and they have a spinner, and they can spin either 1 or 2. And the first one to get to 10 wins. And there was also a color board version of the game. So it's the same game, except just with colors, not with the numbers, in the colors. In the numerical version of the game, the child's task was to say the numbers that they were moving. So for example, if the child was on 4 and spun a 2, they would have to say 5, 6. And if they didn't know what to say, the experimenter would prompt them and say 5, 6. And then the experimenter would say, okay, you were on 4, you spun a 2, what do you say now to move your token? And the child would say 5, 6. And that was the training procedure. If they're on the color board game and they're on the same space, which is purple here, and they spin a red, they would say blue, red. And so they're learning something one way or the other. In one case, they're learning about numbers. In the other case, they're learning about colors. And if the child didn't know the numbers, the experimenter would say in that example, blue, red. And then now it's the child's turn, and the child would have to say blue, red. So in the first large study that Geetha, Ramani, and I conducted on the effects of this board game, we studied 124 children. They were all from low-income backgrounds, they attending Head Start centers. Some of the children randomly assigned played the number board game, some played the color board game. There was a pre-test, a post-test, and follow-up at 9 weeks after the training. And the tasks on the pre-test and post-test and follow-up were number identification, where we show the children numbers and say, what number is this? What number is this? What number is this? Magnitude comparison, where we, for example, say 4 and 6, which one is bigger? Number line estimation, where we have 0 at one end, 10 at the other, and say, where does 4 go? Where does 6 go? And so on. And counting, where we ask the children to count from 1 to 10. We gave these tasks because these were skills that children could learn in the process of playing this game. I should mention that in the US, this game is very popular among middle income and upper income families. In fact, we did a survey, and it's the second most popular board game in the US, and the most popular game having anything to do with numbers. However, it's not played much in low-income families. Very few low-income families play this game. And so we reasoned that low-income children were especially likely to benefit from this because they had no experience with the game before. And also in the US, the math achievement of children from low-income families tends to be very poor. And we wanted to see if we could help these children. The training involved 4 15-minute sessions that were spaced over 2 weeks. So the children would play 15 minutes of the game, which usually was about 4 or 5 runs through the game each session. So they would, over 2 weeks, they would have wound up playing about 15 or 20 games, going from 1 to 10. And the follow-up was 9 weeks after the post-test. The post-test was right after the final game session. And then 2 months later, we brought the children back and we tested them again to see if they still maintained whatever benefits they had obtained from the game. So here are the results. We looked at the percent correct on different tasks, and we looked at the pre-test scores, the post-test scores, and the follow-up scores. Now, in this particular study, the kids in the number board game were a little better at the pre-test than the kids in the color board game. That isn't the case in any of our follow-ups. We have about 6 published studies that use different particular aspects and versions of the number board and color board game. And this particular one, the kids were a little better at pre-test on in the number board game, but that wasn't true in general. And as you can see in this game and this study and in the other studies, the children who played the number board game learned more. They did better on the post-test and on the 9-week follow-up on all 4 of the tasks. And they did better in identifying numbers, in counting, in comparing which number was bigger, and in estimation of where the numbers were on the number line. In a later study, Geetha and I found that playing the linear board game promotes learning of addition. We also found here that playing a circular version of the game did not do any good at all. It actually didn't help the children. The game has to be linear in order to achieve its effects, which made sense from our point of view because we're trying to get the children to map the physical number line onto the mental number line. And it's much easier to do that transfer if you're doing a linear board game, mapping it onto the linear mental number line than if you're doing a circular game. And as you can see, there was much more transfer to addition too. So we took problems that the children didn't know on the pretest, simple addition problems, and we presented feedback on them. And children who had previously been in the linear board group condition learned more of the arithmetic problems than children who had been playing the circular board game. So we found a number of subsequent results in different studies with the board game. That we found that playing the numerical board game improves the learning of low-income preschoolers more than ones from middle-income families, as we hypothesized, due to the games being less familiar to the low-income children. We also found that the game is effective when it's played by Head Start paraprofessionals in small groups. Then we usually had done the studies with graduate students and trained research personnel. But if the game is going to be used in the general environment, you're not going to have grad students and trained research personnel available. And so we wanted to see if the people who most plausibly would be implementing the game, namely paraprofessionals, which are like aides to teachers, whether the children would benefit when they played the game with the children. And the answer was yes. And Alida Lasky and I found that the game is effective on a 0 to 100 board, as well as the 0 to 10 board, and that counting on is crucial to success of the game. So we tested whether it was important that the children say, for example, 37, 38, 39, 40, 41, rather than 1, 2, 3, 4, 5 when they move the pieces. And the answer, as we predicted, was yes, because you don't learn about the bigger numbers unless you say the numbers, just like you don't learn about the smaller numbers on the 0 to 10 game unless you say them.